Hey guys, this is Maths Recovery with Rebecca. Hopefully my sound is clearer on this video. I know with the first one that I posted it was a bit fuzzy. I think that I have got my mic sorted out for this video, which is great. We are going to be looking at trig equations. This is part 2. We are going to be focusing today on linear equations. I remember in the last video I spoke to you guys about degree, and I asked you to just go do some research about what it is and how it impacts on an equation. I don't think I asked you to look at that second part, but we are going to be looking at that today. So we're going to be starting off with something very basic. First of all, I want to just recap on the restrictions on the ratios because I can't explain how important this is for you to understand. Remember from the last video, sine's highest is 1, lowest is -1 on the y-axis, right here. Same with cos. The highest is going to be 1, lowest -1. We can't go above 1, can't go below -1. And then the tan function is continuous on the y-axis. There we go. With its normal asymptotes restriction. And remember period, sorry, 360, 360, and 180. Great. Hopefully you've got that all written down from our last video, and we can start. Let's now look at what linear equations are, just in general. Because if we understand the basics of what a linear equation is, right back from grade 7, we'll have a better understanding of how to approach the trig equations. So let's take a look. So when we spoke about degree 1 in the last video, or degree in general, I'm talking about the highest exponent. So let's look at all of these variables. My highest exponent is 1, my highest exponent is 1, my highest exponent is 1. When I see that my highest exponent is 1 across the board, I'm working with a degree 1 equation. Now with a degree 1 equation, it's important to know to keep your letters on the left and your numbers on the right. So let's see how we can approach these and go from there. So as we can see, a is by itself with the -5. When I say a is by itself, I mean it doesn't have any coefficient attached. So a coefficient would be this -2. Nothing is attached to a with division or with multiplication. So all I would need to do is just move this -5 over, change its operation, because on this side it is subtracting. So on the other side it will be adding. So I'm dealing with a is equal to 3 plus 5. A is equal to 8. There I've isolated the variable by itself on the one side of the equation. And that is done. Let's look at number 2. Let's isolate x by itself on the one side of the equation. -2, that's a multiplier. The operation happening on this side is multiplication. What is the inverse operation of multiplication? Because we're going to be moving it over the equal sign. So the inverse operation is divide. So this is going to be x is equal to -6 divided by -2. Therefore x, remember, when I divide, it's got the same situation as multiplication. There we go, couldn't find the word. Minus divided by minus is a plus. 6 divided by 2 is 3. There again, I've isolated x by itself. The variable is isolated by itself on the one side of the equation. Let's look at the last one. So we've got 5 being divided. Now, what's important to understand here, I've got many operations happening at the same time. Remember, you've learned how to do BODMAS. Now, when you're working with an equation, so you have an equal sign somewhere, you'll be looking at BODMAS backwards. So we'll be going this way. If you are working with an expression which has not got an equal sign attached to it, then you'll be working with BODMAS forwards. So at the moment, we're going to be working with BODMAS backwards. And I'll ask you this. Is there anything that when moved over the equal sign is going to do a subtraction? No. Is there anything when moved over the equal sign going to do an addition? No. Is there anything when moved over the equal sign that is going to do a multiplication? Yes. Here is a division right here. This division of 5, when moved over the equal sign, will do a multiplication. So that is what needs to be moved first. There are common errors that happen here where people try and move the 2 first when it doesn't work. BODMAS backwards. Multiplication over the equal sign will occur before division over the equal sign. So this is what I'm dealing with. So I've got 2x is equal to 50. Now I ask myself, is there anything when I move over the equal sign that division will occur? Yes. Here's a multiplication. 50 divided by 2. X is equal to 25. Again, I've isolated the x by itself on the one side. Now this is a very basic understanding of what we need to do when we're looking at trig equations. But now our variable is not just going to be x. Our variable is going to look like this. Cos x is going to be, our variable. Oh, I'm shaking. Again, yeah. Cos x is going to be our variable. And let's look. Linear equations with trig. Very common in grade 10. It's the beginning of it. It's recognized by first degree equation, which means that our variable of x will be a degree of 1. So cos x will be just cos x, not cos squared x, not cos cubed x, just cos x. This will mean that you'll have one reference angle. Like these questions over here, you only had one answer for x, one answer for a, one answer for x. The degree of the expression tells you how many solutions you will have. So you will only have one reference angle. But this is where the confusion comes in. You will have two general solutions, because remember, when we're dealing with a Cartesian plane, cos occurs in two places. Now, if we draw this over here, the cos diagram, where does cos occur? But now, look at this. Where does cos occur positively? Cos occurs positively in quadrant 1 and quadrant 2. And that is why we will have two general solutions. There are two places on the Cartesian plane where cos occurs positively. When we look at number 2, I'll ask you, where does cos occur negatively? And you will know, because I'm going to tell you where it occurs negatively. Okay, so let's look at this first one. Let me change my color here. Let me change it to green, just for fun. Okay, so first things first. Remember, with the equations before, I had to isolate the variable by itself on the one side. If I look at 1 and I look at 2, the variables are isolated by themselves. Doesn't make a difference on which side, but luckily for us, they are isolated by themselves on the left-hand side. Just looks neater. Okay, so the next thing that we need to do is find the reference angle. So what you need to know about a reference angle is that a reference angle is always acute. Always acute. And what did we say originally on the video before this? Acute angles happen in quadrant 1 between 0 and 90, which means that our reference angle will always be found in the positive quadrant, quadrant 1. So let's take a look. How do I find a reference angle? So you've got this beautiful little button on your calculator, which allows us to arc cos, arc san, arcsin, or arctan. Okay, so all you would need to do is press shift on your calculator and then press one of the ratios, either cos, sine, or tan. And when we press one of these ratios, it's going to look like that, and it's going to open a bracket for us. And what we'll do is we'll just put whatever the y value is that they gave us. In our case, this y value is 0.56. We will put that in our calculator. So I'm going to do that on my calculator, cos -1 or cos arc cos. So my calculator, I'm just going to press shift cos, and you'll even see it's in yellow on your calculator. Just above the cos button is cos -1. And then I'm going to put 0.56. Close the bracket and press equals. I'm just going to get, let me just write this. This is what you're going to write on your calculator. You're going to get 55,94. So we're always just going to round off to the second decimal. Okay, so now this is the acute angle where cos occurs. It'll be the reference angle. It's the starting place. We always start in quadrant 1. Now, we originally said that this equation is representing positive aspects for cos. And we know that cos is only positive in quadrant 1 and 4. So I'm going to write here Roman numerals, quadrant 1. So what do I know? What angle are we looking for? We are looking for x. So in grade 10, you would stop by just finding this 55,94. There you'd be done. In grade 11, we go a little bit further, where we go and look at the generalized solutions of these equations. Now, the word general solution is quite nice because in grade 11, we worked all over the Cartesian plane. We even went past 360. We looked at 720, or we looked at 1,000 and something. I don't know, 360, lots of 360s happening in there. And then we reduced it and we went back into our 360 circle. But at the moment, we need to find a generalized formula for all those solutions, those 720s, those millions of solutions, because we can go round and round, around and around and around and get a bigger, just like many circles just on top of each other. But for now, we're just going to stick in this circle, and we're always just going to stick in from 0 to 360. So, where are we? Quadrant 1. What do I know? Quadrant 1 is just theta. What did I calculate theta to be? Well, 55,94 degrees. And then to compensate for all of those solutions of us going around and round and round, we're going to add k times 360. And luckily for us in the school, we are only going to work with k when k is an integer. When I say z, that z right there, it's actually supposed to look something like that, is referring to integers. So basically what happens here is you will go and maybe put a 1 into k, and then you'll get a solution. Just substitute 1 in, you'll get 55,94. That's the first place where the solution is going to occur. Maybe you want to put a 2 in there, and that's going to actually find us another solution of x, again in quadrant 1, but with a whole nother 360 going on there. So when you put 1 in, you get the first revolution. If you put 2 in, you get 2 revolutions to this place right here. Because we know that originally it's 55,94. And if we go around again in that circle, let's say we put a 1 into k, go around again, we'll just go 360. Adding to this 55,94 is going to give me 415. So that's just another solution if we go 1 360. What if we go 2 360s? Our second solution is going to be 775 degrees. So obviously in school we don't go this big. We try and keep it between 0, 180 or 0 and 360, but it's just to show you what the importance of this k times 360 is. Okay, so now we initially said that there's two solutions here. The other solution is going to be in quadrant 4. X is equal to, now what was the reduction in quadrant 4 over here? The reduction in quadrant 4 was 360 minus theta. Remember I said we need to try and stick in the 180 and the 360 quadrants. Just stay away from those 90 minus and 270 minuses unless we really need them. We're just going to stay away from them. So this is going to be 360 minus our original degree, because theta is always acute, plus k times 360, and then k's. Okay, and then we're just going to find out what this is. What is 360 minus 55,94? On my calculator, I'm getting 304. Okay, I'm going to write it over here. It's 304.06. Sorry, we always need to round off two decimals. I'm just like writing in the smallest little space here right at the bottom. Let me just see, 06 plus k times 360. And again, that just puts us in this place right here of, if I go around positively, let's say I go around like this, that's going to leave me with 304,06. It's actually really bad drawing. It should be a little bit, it's not too bad because that's 270. If I go and I put a 1 into k, that's just going to put me around again to the same spot, just adding 360 to this. What's that going to be? 664. Okay, so it's just going on and on and on in a circle. Now, let's look at the second example. I'm just going to rub all of this out here, make our life a little bit easier so we can see what's happening here. Okay, so let's take a look. It is now saying to us that cos is negative, which means that where is cos negative? Well, we know this is where cos is positive, these two. So obviously in these two, cos will be negative. And what are the reduction angles in these two? This is going to be 180 minus theta, and this is going to be 180 plus theta. And what did we say initially about the reference angle? It's always acute. Now I just want us to test something out. Let's just go inverse cos. And I put the negative in. Now those of you that know what's happening here, big red flags all over the place, do not put the negative in to find the reference angle. But some of you don't know that. So let's just go and test that out. Let's say that I go and put the negative in here. And I press equals, and now I'm getting 124,06. Now my question to you is this. Is this an acute angle? No, it's not. This is going to make us sit somewhere over here. Because remember, this was 90, and this is 180. So you're actually sitting in quadrant 2 as your reference angle. And what do we know? The reference angle always needs to be acute. So this is incorrect. So a nice way for you to remember it is always use the positive of whatever you've got going on here for the y. That negative right there is just telling you which quadrant you are going to be in. And in our case, we are going to be in quadrant 2 and quadrant 3. So I would just do my reference angle, and we are just going to get 0,56. We're just going to get exactly what we got in the last one, 55,94. And now we know, because it's negative, we're going to be in quadrant 2, which we know is going to be 180 minus 55,94 plus k times 360 k's. Let's just work that out. 180 minus 154, 55,94 is 124. Okay, times 360. Cares. Or we're going to be in our quadrant 3, which is going to be 180 plus 55,94 plus k times 360. Cares. So therefore my last solution plus 55,9. This is going to be 235. So obviously you're more than welcome to just pause the video before I even start the questions and just do them yourself and see if you get them. And then just watch, because as I'm busy explaining, there's some interesting little facts that I'll pop through. But let's just look at the last 2 here. They're over there. So you can pause the video and you can start them. But let me just dive straight in. So remember I said that you need to isolate the x, the variable, before you can even start. And also we're dealing with 1,28. We should know right away that 1,28 is off sine x's original mother graph. I mean, we said originally that sine x can only go from 1, not higher than 1, to -1, not lower than -1. So we already know that we need to do something. And if we're following BODMAS backwards, what was it? Let's just write it over here. Is there anything that when I move it over the equal sign, it's going to do a subtraction? Well, there it is right there. So this becomes -1, 0,28. Is there anything that's going to add? No. Anything that's going to multiply? No. Anything that's going to divide? Well, there's a times 2. When I move it over, it's going to divide. So 0,28 divided by 2, that's going to give me 0,14. 0,14. Great stuff. Okay, it's a very small length, but it's okay. Let's look at our Cartesian plane. We can see that this is positive. This is positive right here. Where is sine positive? So if I draw my little cast diagram here, I know that sine is positive in quadrant 1, which is just theta, and quadrant 2, which is just 180 minus theta. Again, it's degree of 1, so you're going to have one reference angle, but two solutions. First solution is going to be in quadrant 1. So that's just going to be, it's going to be x, because we've got to just use the same variable that's over there. I haven't found my reference angle yet, guys. Let's go find the reference angle. I just jumped straight into it. Let's go and find this reference angle. Sorry about that. Pen. So remember what we do, sine -1, 0,14. And I've got to just make sure that it's acute, inverse sine, 0,14. And it is very small actually, it's very acute. So that's going to be 5 degrees, and now we can start. So in quadrant 1, it's just going to be x 8,05 plus k times 360 cares. Or we're going to be in quadrant 2, x is equal to 180 minus 8,05 plus k times 360 cares. So x is just going to be 180 minus 8,05, and I'm getting 171,95 plus k times 360. Okay. Let's look at this one over here. Now, this is where we have a bit of a situation here because all of these, we had the x by itself, nothing attached to the x via bracket. Here we've got an x attached to the bracket, or a negative 45 degrees attached to the bracket. Okay, so it's very important to understand that if you have a degree attached to the bracket, it's actually attached to your solutions. So let's just do what we normally do. Look at BODMAS, no subtraction, no addition, no multiplication. There's the division. So I'm going to have sine x minus 45 is equal to 2 divided by 3. Now 2 divided by 3 is less than 1, so it's perfect. Now, when I do my reference angle, I need to understand that this x minus 45 is going to only play a role in my solutions. So I still need to find my reference angle. And then when I go to my solutions, because I can see this is still positive, so I'm still going to be in quadrant 1 and 2. When I go to my solutions, instead of just writing our x here, like we normally did, we're going to write whatever's there. So x minus 45 is equal to 41,89 plus k times 360. Cares. X is going to be, remember we're going to move the 45 over and we're just going to add it. And I'm going to get 86,81 plus k times 360. Or I'm going to be working in quadrant 2. So I'm going to go x minus 45 is equal to 180 minus 41,89 plus k times 360. No one cares. X is going to equal to 180 minus 41,89 plus 45. 183,11 plus k times 360. Okay, so for tan's exactly the same. You would just do your two solutions. I actually should have added in a tan here. I apologize for that. But tan, sine, cos, all the same method. It just depends on what is hanging around with the numbers. Okay, but you treat it as you would a normal linear equation. Maybe I should do some more of these number 4s in another video where we've actually got maybe a 2 attached to the x, and we can see why we don't actually let this 45 affect from the reference angle. But we'll look at that maybe in another video. I hope you guys have a great day. Hopefully this video was very informative and we are able to look at quadratic equations going forward. Knowing this basic information on linear equations for trig is very important. So thank you for sitting through my video. I know it was quite long, but having this basic information, like I said before, is very important. Thanks so much. I will see you in the next one.